So hi everyone, in this video I am going to discuss about graph isomorphism. So the simple graphs G sub 1 and G sub 2. So when we say simple graphs, what do we mean by that? So it's basically just a graph that do not have multiple edges, do not have any loops, and things like that. So we have two simple graphs, G1 and G2, and we can say that these two are isomorphic if there exists a one-to-one and onto na function f from v sub 1 to v sub 2 with the property that a and b are adjacent in G1 if and only if f of a and f of b are adjacent in G2 for all the vertices of a and b in V1. So what we are saying here is that we have to create a mapping between the vertices in G1 and the vertices in G2. Okay, and we must make sure that it is one-to-one. That means that exactly one element is mapped from G1 to G2 and vice versa. Okay, and if A and B, let's say, are adjacent in G1, then the vertex that is mapped to A and B must also be adjacent. Okay, so it might sound complicated right now, but let us have a better example. So anyway, going back to these graphs. So we have a graph G1 consisting of vertices A, B, C, and then D. And then we have also a graph G2 consisting of 4 vertices A, E, F, G, and then H. So can we say that these two are isomorphic? So basically, the definition sounds a little bit complicated, but it basically means that the two graphs have the same structure. Okay, so if we try to morph G1 to G2 and G2 to G1, we can see that they are basically the same. Okay, going back here and then going back here. So see, they have the same structure. And even if you move the vertex E here and the vertex G, if we stretch E and G, still they have the same structure. Okay? Yeah. Anyway, let us more formalize this property. So we said here that there is a one-to-one and onto function f from the vertices V1 to vertices V2, or the V1 is all the vertices in graph 1 and V2 is all the vertices in graph 2. Okay, so we have to create a mapping. So let's say we can map A and then F. Okay, so we can then say that f of A is equal to F, and then B may be mapped to E, and C may be mapped to G, and then D may be mapped to H, right? So as you can see, there is a one-to-one mapping. So exactly one vertex in V1 is mapped to exactly one element or exactly one vertex in V2, okay? And we also said that the function must be on 2. Okay, so all that means that all the elements in or all the vertices in V2 is mapped to a vertex in V1. So essentially, let's say we have another vertex here, vertex H, vertex I, and then we connect it to H. Okay, so basically we have to add here another vertex in V2 and we name it as I. However, this vertex I in V2 is not mapped to any vertex in V1. Okay, so we can say that the relationship or the function is on 2 because this is the definition of on 2. All the elements in V2 is mapped to an element in V1, right? And we can also see that from here, they do not have the same structure, correct? Why? Because this graph has only 4 vertices, but graph 2 has 5 vertices. And then we have that extra vertex that is connected to another vertex, and that is not found in the graph G1. So can we say that they have the same structure? No. Okay. Now, we haven't explored this property yet. So we have explained why it is 1-to-1 and it is on to function f from v sub 1 to v sub 2. But with the property that A and B are adjacent in G sub 1 or the graph 1, if and only if the elements they are mapped to are also adjacent in G2. Okay, so let us explore that more with an example. So let us start from here. So A is adjacent to B and then C. And then as you can see, A is mapped to F, B is mapped to E, and then C is mapped to G. So if A is adjacent to B and then C, that means that F must be adjacent to E and then G. So as you can see, we follow this property, we fit into this property. So we move on to the next vertex. So B is adjacent to A and then D. And we can see that B is mapped to E, A is mapped to F, and then D is mapped to H. And if B is adjacent to A and D, then E must be adjacent to F and then H. And it is true. So we move on to the next vertex, C. So C is adjacent to A and then D. And C is mapped to G, A is mapped to F, and D is mapped to H. So as you can see, C is adjacent to A and D. And C, which is mapped to G, must also be adjacent to F and then H. And since this is true, so we move on. And then for D, D is adjacent to B and then C. And as you can see, D is mapped to H, and then B is mapped to E, and then C is mapped to G. And since D is adjacent to B and then C, so H must also be adjacent to E and then G. And since this is true, so we have proven that we have a 1-to-1 and onto function from function f from v1 to v2 such that every edge every edge in graph 1 is also the same with graph G2, or that if A and B is adjacent in G1, then f of A and f of B are also adjacent in G2. So we have proven all of those. Okay, now moving on. In summary, we can say that this graph G1 is isomorphic to graph G2 since they have the same number of vertices, which is equal to 4, and the same number of edges, which is also equal to 4, and the same number of vertices of degree k. So if you look at every edge that is incident to every vertex, so it is equal to 2 in graph G1, and it is the same with graph G2. All right? Yeah. So now, what about these graphs? So can we consider this as isomorphic? So what is the difference from the previous example? The only difference is that there is an edge between A and D, which is not present in the previous example. So can we say that these two are isomorphic? So let's say we have a mapping from A to F, okay? And we can immediately see that there are 3 edges that are incident to A. And in F, there are only 2 edges that are incident with F. Okay, so we can then say that A has a degree K3 and F has only K equals 2. And this is also true for vertex D. D, which is mapped to H, in D has a degree K equals 3, but H has degree K equals 2. And what's an easier way to look at it is to count the number of edges and the number of vertices with degree K. So from here, we can already see that the number of edges in graph 1 is 5, but the number of edges in graph 2 is only 4. So we can say that immediately it hasn't retained this property, and therefore they are not isomorphic. Okay, Now, assuming that we have this another graph. Okay, so are these two isomorphic? So let us create another mapping. So A is mapped to F, B is mapped to E, C is mapped to G, and then D is mapped to H. But then we have another vertex here in graph G2, which is I. But I is not mapped to any vertex in V1. So we can then say, or we can see here that the graph is, the function rather is one-to-one, but not an onto function. Because we have an element here in V2 that is not mapped to any vertex in V1. Okay? And an easier way, a much easier way to see it is that first, from the count of vertices pa lang, so we can see that in graph G1, we have 4 vertices, but for graph G2, we have 5 vertices. So immediately, it has not retained that property. And therefore, we can say that these two are not isomorphic. Okay?